Yo, what up, y'all? I'm here with the Chapter 2 EOC review and retake prep packet. Making this video hopefully to help you out if you want to take the Chapter 2 retake, and then this will also help review for all the Chapter 2 stuff on the end of course. Let's get it poppin'. What we've got is we're working with functions. We are taking these basic functions and transforming them in different ways. I'm going to show you a little sketch of each function. Quadratics form this nice little parabola. Cubics have this curve in them. This point of the quadratic is called the vertex. This point on the cubic, the center, has a fancy term called the point of inflection. It's a calculus term that describes like it changes concavity, but you can think of that as kind of like the vertex. It's the center. Absolute value functions are where everything is positive and it makes this sharp V. Square root functions are where you can't square root a negative number. It gives you like something weird and imaginary. So x being negative doesn't really work. This starts at 0 and then goes on to the right from there. It doesn't increase very quickly, so I try to show that in my sketch. Rational functions are strange. They're the ones where it's 1 over x. X is in the denominator. And when you have 1 over 0 in math, it doesn't really mathematically make sense. It's called undefined. So this line gets split into 2 pieces. The equations for these functions are pretty much all the same. You got to know all 5 of them, but you'll see in a second that you kind of can just use one and apply it to all of them. They all start with y equals, or f of x equals. They all have an a in the front. They all have an x minus h. The only thing that changes is what's happening to the x minus h. For quadratic functions, the x minus h is being squared, and then there's a plus k on the end. Cubic functions have the exact same equation, but now the x minus h is being cubed instead. Absolute value functions have the same equation, except now the x minus h isn't an absolute value. You can probably guess what's happening with square root functions. It is the same equation, but the x minus h is under a square root. Rational functions, you've got that a in the front. The x minus h is in the denominator of a fraction, and then plus k on the end. You may also see the a just on top of the fraction, and we'll see that in just a second. Okay, so those are the 5 functions. Let's see how the a, h, and k affect those. Looking at this function here and comparing it to the fundamental functions, I could see that this in the very front is the a, this in the parentheses is the h, and the k is on the very end. The type of function is what's happening to the x minus h. It has that squared, so this is a quadratic function. My a in the very front there is 3, which stretches the function. My h, I'm going to keep it going. My h is inside the parentheses. It used to be x minus h, now it's x minus 5. Hopefully you can see that that subtraction, that minus, was already there. So this h is not actually negative, it's just positive. So it goes to the right. That k on the end is positive 4, so it goes up. This function's vertex was originally at 0, 0, then it got moved 5 to the right and 4 up, so now the vertex is at 5, 4. Awesome. And then using this, I would be able to graph that really easily. I'll show you that in a second. This looks like a cubic function, this g of x. I've got that cubed. The a is in the front, 1/2. If it is a big A, like 3 or 5, it stretches. If it is a small fraction like this, it is called compressed, and it gets wider. The h, it used to be x minus h in there. So this h must be a -2, because if it's x minus -2, that's what becomes positive. So the h is like the opposite of how it looks. You can think of that. The k on the end, -10, that's going to move it down. That point of inflection is at hk, -2, -10. Cool. This is a square root function. You can tell because of the square roots. The a in the front here, you can't see, but there's a little invisible 1. The a is -1. It's not going to stretch or compress because the a is just 1, but that being negative is going to reflect across the x-axis. In simple words, it flips over. It's upside down. Same thing with this g of x. That h kind of looks positive, right? It's x plus 7, which means that it actually is negative, because there should be a negative there. It should be x minus h, but it got changed. So that's going to go left 7. The k, I don't see anything. There's a hidden +0. So it doesn't go up or down. The vertex, the starting point of this square root function, -7, 0. Cool. This is a rational function. I can tell because x is in the denominator. The a is up top there. That is 10, which is going to make this function real stretched. The h down here, x minus h, is +3. And the k is, 100. It's going to move way up. So the vertex, the center, is at 3, 100. Okay, I'm going to use what I know about these functions and the fact that their most important points are at hk to graph them really quickly. This function, I see that the h is 1, +1, and the k is -2. That is my vertex. That is the center of this quadratic. So I don't really want to mess around with plugging in random numbers. If I know that my vertex, the center of my parabola, is at 1, -2, I'm going to plug in a value right next to it on either side. So I'm going to plug in x equals 0 and x equals 2. What you do to plug those in is just one at a time, take that x value and replace x with that number. And then we've got some PEMDAS. 3 times 0 minus 1 squared minus 2. I do the parentheses first, so that'll be -1 inside the parentheses. Let me write this out. Then I do the exponent, which is -1 squared, which just gives you 1. And then I have 3 minus 2, so this is 1. I do the same thing and plug in 2 for x. You do that algebra, you'll end up getting 1. So I just found new points. When x is 0, y is 1. That'll go right there. When x is 2, y is 1. That'll go right there. Bada bing. That is this parabola. I don't need to put any more points to make that more accurate. That looks great. Okay, I'll do the same thing with this absolute value function. Looks like the h is -1, the k is 0. So when I make my table xy, I'm going to put that in the center, and I'm going to plot 1 point on either side. One where x is -2, and one where x is 0. So when I plug those in, it'll look like that. The absolute value here, let me see. -2 plus 1 is -1. The absolute value of -1, anything in there becomes positive. So it's just 1. So the y value when x is -2 is -1/3. I'll do the same thing and plug in 0. And you end up getting the same value of -1/3. So when x is -2, y is -1/3. When x is 0, y is -1/3. If I wanted this to be super accurate, I could go and plug in maybe one more point. Like I want to know where the y value is when x is -3. If I were to plug in -3, I would get, let's see. I would get negative 2/3. So this is very wide, like that. The more x values that you plug in, the more accurate that your function will be, but you can get by with just the most important 3 and be good to go. Okay, last one, this cubic, the h, I don't see nothing. It just goes straight to x cubed, so there's no h in there, which means that it's 0, and the k is negative 1. So that is my point of inflection. That's my center point. I'm going to put that in the middle of my table. 0, negative 1. I'll plot that. And then I'm just going to plug in negative 1 and positive 1. If I plug in negative 1, I get 1/2 times negative 1 cubed. Negative 1 cubed is negative 1 times negative 1 times negative 1, which comes out to negative 1. And then I multiply that by 1/2 to get negative 1/2. Minus 1, this will be negative 1.5, or negative 3/2. I'll do the same thing with 1. 1 cubed is just 1, and it's going to be 1/2 minus 1, which comes out to negative 1/2. So when x is negative 1, y is negative 1.5. When x is positive 1, x is 1/2. I'm going to do what I said earlier. I'm going to plug in 2 for x and just see what the y value would be. 2 cubed is 8, so I have 1/2 times 8 minus 1. And I find that when x is 2, y ends up being 3, so it's already all the way up here. And that gives me a way better image of what this thing is going to look like. Just like that. Awesome! Woof! Oh my gosh. Okay, keep it moving. Stretched by a factor of 3. This is a cubic function. I'm trying to create the function like this. So what I'm going to do is I'm going to use this equation. I'm going to take the a, the h, and the k, and create the function. So stretched by a factor of 3, my a has something to do with 3. Reflected across the x-axis, that means the a is negative. Shifted 5 units to the left, that means h is negative 5. 2 units down, k is negative 2. Now that I know my a, h, and k, here's my equation for a cubic. I'm just going to plug those 3 values in where they appear. Just like that. Here's my x minus h. It's x minus negative 5. I don't like how that looks. It's the same as adding. That is why when you have a negative h, it flips from a negative to a positive. Okay, let's see this one. This is a quadratic, so I'm going to use the quadratic equation. Compressed by a factor of 1/3, so my a is 1/3. 9 units to the right, h is 9. 3 units up, k is 3. I'm using my quadratic equation, so I have a x minus h squared plus k, just like that. Awesome. Okay, bringing all of that together, this is the most important part of this chapter, using what we know about functions and a, h, and k and the vertex to model a situation using a function. So the video that I showed in class is Buddy the Elf throwing a snowball at a kid super far away. I'll draw a little picture. Here's my x and my y axis. I'm going to draw Buddy throwing his snowball. The situation that I got from the video is that the snowball travels 200 feet in total. So I'm going to put a 200 with a point right there. That is where the snowball hits the kid. I'm going to put another point at 0, 0. That's where Buddy throws the snowball. And then what else do I know? At its highest point, halfway through the flight. Halfway through the flight would be 100 feet away. If it goes 200 feet in total, halfway through would be 100 feet. Halfway through its flight, it is 10 feet in the air. I'll use the y-axis as like in the air. So when it is 100 feet away, it is 10 feet in the air. That is the highest point. So I can use that to draw a rough sketch of what this throw looks like. Then I'm going to use that information to create a quadratic equation for this. So quadratic equation, y equals a times x minus h squared plus k. If I want this quadratic equation to match this snowball toss perfectly, I need the a, I need the h, and I need the k. The problem is I cannot tell what the a is just by looking at this. So what I've got to do is plug in the h and the k. I can tell what the hk is. It's always at the highest point, the vertex right there. So I know that h is 100 and k is 10. Bada bing. If I want to mathematically figure out what a is, I would have to plug in for x and y so that I could solve for a. And the x and y comes from some other point on the function. I could use 0, 0, or I could use 200, 0. I'm going to use 200, 0. So x is 200, y is 0. I plug all 4 of those values in, and it looks like this. And now I have an equation with only one variable, which means I can solve for it. What I've got to do is, inside the parentheses, 200 minus 100 is 100. 100 squared is 10,000. And then I want to get x or a by itself. I cannot add these two things since this 10,000 is multiplied by a. They're like tied together. So I can subtract 10 on both sides. I'm going to bring it over here. So I have negative 10 equals a times 10,000. My last step to get a by itself, it's being multiplied by 10,000. So if I divide by 10,000, that'll give me just a. So a is negative 10 over 10,000. I can reduce that to be negative 1 over 1,000, but who cares? So there's my a. I had my h and k from earlier. I was only using the x and y. I was taking advantage of them to figure out what a is. Now that I have a, I don't care about them anymore. I rewrite my equation with a, h, and k. So y equals a, which is my negative 10 over 10,000, times x minus h. I turn x and y back to x and y, squared plus k. That is the quadratic function that models Buddy the Elf's snowball toss. Using everything that math is capable of, calculus and physics, we could figure out how fast this ball is traveling, how long it's in the air for, the distance it actually traveled, all sorts of things. For example, we can figure out how high the snowball is when it's 150 feet away from Buddy. Based on my drawing, it looks like I used the feet away from Buddy as the x, so this is going to be my x value. So all I'm going to do is I'm going to take my new fancy function, and I'm going to plug in 150 feet away from Buddy. That'll tell me how high it is. So inside the parentheses, I have 50. I'm going to keep it going over here. 50 squared is 2,500. So then I can multiply negative 10 over 10,000 times 2,500 over 1. And you get negative 25,000 over 10,000 plus 10. Negative 25,000 over 10,000 turns out to be just negative 2.5. And then I have the plus 10. I add those together. I get 7.5, and that is feet above the ground when it is 100 feet away from Buddy. If I double check my graph, here's about where 150 feet is, and that sounds reasonable. If the highest point was at 10, it makes a lot of sense that it's dropped maybe about 2.5 feet to get to there. Okay, so that looks perfect. That is everything that you need to know about Chapter 2, Transforming Functions. Let me know if any of this was tricky, and we could get you all set before you retake that test or before we take the end of course. All right, let's get it. Thank you so much for being here. I really hope that this is something that helps you. Let me know if it is, and maybe this is something I could keep doing for you. Okay, see y'all in class.